It's November in Vancouver, and the gray sky draws in around the windows. I actually appreciate weather like this. It's good for studying and reading. I'm sitting in a room in a library, surrounded by my peers, who are 6 years my junior, but infinitely more knowledgeable, and I'm taking a break, reading a book. The book is called The Life Ascending by Nick Lane, and it's my translator and guide as I navigate this wild new world of science. Most of the time, when scientists tell their story, they say they've loved science their whole life. My parents were engineers. It should have been a slam dunk. But this was not me. Sure, as a kid, I loved predicting the weather and reading books about volcanoes, but I always struggled with math and science in school. I loved writing and words, though, and they were pretty easy. So that, combined with some confusing advice from my parents and teachers, is how I wound up getting a bachelor's in linguistics. Friends, I hated it. The amount of time that we spent talking about the fun stuff like word origins and how we could make every conceivable sound in human language was woefully brief. Instead, every semester, we'd take 1 or 2 theory classes only to be told the following term that what we had learned was wrong. It happened so often it gave me trust issues. In the end, I found a niche that seemed rewarding and fun, but I couldn't shake that feeling that I had just wasted 4 years becoming something I didn't want to be. I'd always planned to go to grad school, but I took a year out to figure out what my next move should be. Should I continue in linguistics, even though I hated it, and try to forge a path in academia? Not ideal. Should I abandon academia altogether? I honestly never considered it. Perhaps, though, I could get a degree that would be a bridge between what I knew and what I cared about, which increasingly was neuroscience. Through some miracle, I got accepted to my dream school to do a master's in linguistics. I know you're like, Kate, we talked about this, but hear me out. I thought I could finagle a collaboration with the neuroscience department. So for months before the course began, I studied neuroscience after work every night, determined not to be behind when I arrived. But when I started, there was no neuroscience. Worse, the people I'd hoped to work with didn't even respond to my emails. I was just watching my plan disintegrate. And then it happened. It was not a good thing. One cozy and snowy December afternoon, I was chatting with a friend over a cup of tea, and I watched him slip into a depressive episode. We'd been talking about how it felt for him and just comparing notes about our mental health struggles. He said it began with a feeling of dissatisfaction in his chest, which would then radiate upward and engulf him in sorrow and immobilize him in despair. We sat in silence until the light began to fade, and then I gently guided him home. While his mind had slumped into stillness, mine had started to race. What was the relationship between that feeling he had had and the emotion he experienced? Could it be pain? And if so, could you design a painkiller that treated depression? In between my studies and my concern for my friend, I scoured the literature, searching for the answer to my question. While I found evidence of its plausibility, no one had yet described what I was considering. Maybe I would have to be the pioneer. In my searches, I had found a professor at my university whose interests seemed to dovetail with my idea, and I shot him an email, just with a hypothesis and evidence like, can I help you solve this problem? He responded almost immediately, though. This was really interesting. What department was I in? The Life Ascending, which, by the way, is about 10 traits that evolved and shaped life on Earth, turned out to be more than just a guide. It was also a gateway drug. You see, when I told that professor that I was a linguist, he had replied with a short but kind email. If I wanted to do the work, I needed a background in biochemistry. And I don't know if it was the urgency of my friend's situation or my irrepressible frustration with linguistics, but I overcame my fear of science and I applied for a biochemistry degree, and somehow I got in. I cannot describe how overwhelming cell biology and chemistry are when you know literally nothing about them. And I have never fought harder to understand something with less of a clue of how it all fit together. The Life Ascending provided a framework on which I could assemble that wealth of knowledge, and it provided context to inspire wonder. I was particularly fascinated by chemical gradients and cell membranes, which sound weird and esoteric, but they are the essence of life. These proteins within cellular membranes control chemical movement, and through this regulation, cells generate energy and communicate with one another and move nutrients and waste products through their compartments. Better yet, they are integrally involved in neurotransmission and sensation. This was it. This was the path to victory. That was in 2015. Now, I study membrane proteins here at Caltech. Mic drop. End of talk. No, but seriously, I went down this rabbit hole and I never looked back. Membrane proteins are not just integral components to my original question, they are crucial drug targets for many other pathologies, in part because of their accessibility on cell surfaces, and in part because they contribute to many, many essential processes. But Kate, you say, if that's the case, why don't we already know everything about them? Well, folks, they're just really hard to study, which I'll admit is actually part of the thrill. See, membrane proteins are incorporated to some extent into the lipid bilayers of the cell, and so they need to be both oil-loving and water-loving. And as anyone who's ever made salad dressing knows, oil and water don't mix. It can be really hard to find conditions outside of the cell that these proteins are happy in. It gets even more exciting when you want to figure out a model for your protein. So proteins are three-dimensional chemical machines. Some of that chemistry holds them together, some of it interacts with other things, and some of it catalyzes reactions. And as you can imagine, when this machinery is interrupted, there can be catastrophic consequences. Take cystic fibrosis, for example. It's caused by a single mutation in the chloride channels that are found throughout your tissues and help move water across membranes. One mutation, and they don't work anymore. Studying protein structures can help us learn how these machines are built and what effects mutations have and how we might be able to fix them. So this is where it gets really fun. If you want to visualize something incredibly small, it turns out you need a machine that is incredibly large and like also futuristic ray guns. Let's talk about two different techniques. So let's say you want to do some old-fashioned, good old structural biology. You're going to use X-ray crystallography. You crystallize your protein, which is basically witchcraft, and then you're going to ship it to a synchrotron facility, which is a particle accelerator, where some guy's going to load your teeny weeny little sample into a holder, and then they're going to fire high energy X-ray beams at it like they're a freaking Bond villain. Nowadays, you can sit back at home with a Red Bull and watch your data come in at 3 o'clock in the morning in real time, and we have software that lets you compute a model in minutes. But back in the old days, people would have to solve a complicated mathematical equation for every point of data. And then they would literally build a physical model, atom by atom, of their protein. Yeah. In 2013, X-ray crystallography's frenemy, electron microscopy, got a glow up in its electron detectors that led to the resolution revolution, which sounds epic, and believe me, it is. So a big problem with crystallography is the whole crystal part, which, for reasons to do with solvents, membrane proteins are not a fan of, which is a big reason why they're underrepresented in our protein model databases. EM presents an interesting solution. How about you take the environment your protein is happy in, freeze it, and then fire high energy particles at it to see what it looks like. Brilliant! So you freeze your protein in its favorite bath bomb on this tiny metal disc full of holes, and the ice stretches across these holes with your protein suspended in them like angels in microscopic stained glass windows. And then you put it in a 12-foot tall electron microscope and you fire high energy voltage electrodes at it, again, like a Bond villain, and then boom, you've got pictures of your protein. It still takes a lot of processing to get a high resolution model, but just think, you can see something that's about 10 nanometers across. That's about 5,000 times smaller than the width of a human hair. I just recently finished getting trained on one of the smaller electron microscopes here at Caltech, and the moment that you dim the lights and open the valves is magical. So, do I regret that I spent 6 years trying to be something that I didn't want to be? Sometimes, yeah. But I've come to view it as an invaluable experience. I've never felt at home where I thought I should, but now I feel wonderfully at home in a field I never believed that I could. Thanks in part to therapeutics that were developed based on work like what I want to do, my friend is doing so much better. And it gives me hope that whatever I discover will make a difference to someone. I cherish the purpose of my research so that even when it's frustrating and nothing works, I love what I do. And I'm confident that wherever I point my electron beam, I will find problems that I can solve. Thank you.